In practice, we often want to accelerate a chemical reaction at fixed temperature. It can be achieved by adding catalysts. The process is called catalysis. Catalysts have two key properties. First, catalysts are not consumed in the reaction and remain unchanged after it. A catalyst is both a reactant and product of the reaction. It generally reacts with one or more reactants to form intermediates that subsequently give the final reaction product, in the process regenerating the catalyst. For example, the uncatalyzed disproportionation of hydrogen peroxide to water and oxygen is slow. Upon the addition of a small amount of manganese dioxide, the hydrogen peroxide reacts rapidly. The manganese dioxide is not consumed in the reaction. Accordingly, manganese dioxide is a catalyst for the disproportionation of hydrogen peroxide. One of the mechanisms of this reaction is that manganese dioxide is reduced by hydrogen peroxide to form manganese 3 oxide in the first step. Then, manganese 3 oxide is oxidized by hydrogen peroxide to form manganese dioxide. Second, catalysts do not modify the overall standard Gibbs energy changes in the reactions. As a result, they do not change the chemical equilibria. For example, the production of ammonia from hydrogen and nitrogen is an exothermal reaction. Its equilibrium constant decreases with temperature. At high temperature, the equilibrium quickly becomes quite unfavorable for the reaction product, regardless of what catalyst is used. In contrast with catalyst, an inhibitor diminishes the rate of a chemical reaction. The process is called inhibition. For example, acetanilide is used as an inhibitor of hydrogen peroxide disproportionation. It slows the decomposition of Drugstow hydrogen peroxide solution. Inhibitors are sometimes called negative catalysts. But since the action of an inhibitor is fundamentally different from that of a catalyst, this term is discouraged. Catalysis can be classified as homogeneous and heterogeneous types. In homogeneous catalysis, only one phase is involved. That is, the reactants, catalysts and products are uniformly mixed in a dispersion such as a gas or a solution. For example, the oxidation of sulfur dioxide by oxygen can be catalyzed by nitrogen monoxide. All of them are in gas phase. In another example, Fischer-Speier esterification takes place in acidic aqueous solution. The catalyst is proton. In heterogeneous catalysis, the catalyst is in a different phase from the reactants and products. The reaction occurs at or near the interface between the phases. Usually, the reactants and products are still in a dispersion phase, while the catalyst is in a solid phase. For example, the production of gaseous ammonia from gaseous hydrogen and nitrogen catalyzed by solid iron is a heterogeneous catalysis. In organic reactions, acid is an important catalyst, as shown in Fischer-Speier esterification. However, liquid strong acids such as sulfuric acid are dangerous to handle and difficult to recover. In industrial-scale chemistry, many processes are catalyzed by solid acids, which do not dissolve in the reaction medium and are safe to touch. Well-known examples include silicoaluminates zeolites, which are strong Lewis acids. When treated with areneous acids, they become areneous acids as well, which can be as strong as sulfuric acid. Zeolites catalyzed reactions are heterogeneous catalysis. Catalysis increases the rate of reaction because it changes the reaction mechanisms. With catalysis, the intermediates of a reaction and their enthalpies are different from those without catalysis. The intermediate with the highest enthalpy plays the role of the transition state, while its enthalpy compared to the enthalpy of the reactant serves as the activation energy. When catalyst is used, the activation energy decreases, so the reaction is accelerated. For example, the production of ammonia from nitrogen and hydrogen in gas phase is extremely slow. The hydrogen and nitrogen molecules must dissociate to react. The dissociation of freestanding nitrogen molecules is particularly slow. In contrast, Haber-Bosch process is the catalysis of ammonia production on iron surface. The reactants adsorb on iron surface, dissociate and react, followed by the desorption of the product. The dissociation of nitrogen on iron surface is much faster. Thus, the production of ammonia is greatly accelerated. An energy diagram can be created based on the enthalpy of reaction of the individual steps. Due to the high activation energy of the dissociation of nitrogen, the gas phase reaction is not realizable. The catalyst avoids this problem, as the energy gain resulting from the binding of nitrogen atoms to the catalyst surface overcompensates for the necessary dissociation energy, so that the reaction is finally exothermic. Nevertheless, the dissociation of nitrogen remains the rate-determining step, not because of the activation energy, but mainly because of the unfavorable pre-exponential factor of the rate constant. Although hydrogenation is endothermic, this energy can easily be applied by the reaction temperature, about 700 Kelvin. Adsorption is the adhesion of molecular entities from a dispersion to a solid surface. The reverse of adsorption is called desorption. The solid at the surface of which adsorption may occur is called an adsorbent. The molecular entity which is adsorbed in an extremely thin surface layer on the surface is the adsorbate. In heterogeneous catalysis, the absorption of reactants on catalyst surface and the desorption of products from it are crucial. The catalyst is the adsorbent. The adsorbed intermediates are the adsorbates. Surface coverage is the number of adsorbates, Na, divided by the number of adsorbates in a filled monolayer on the same surface, N0. There are two cases. If the adsorption occurs on certain sites, N0 is the number of the sites. If the adsorption can occur anywhere on the surface, N0 is the number of adsorbates in two-dimensional close packing on the surface. Generally speaking, the coverage depends on the concentration of molecular entities in the dispersion, the interaction between the adsorbate and the surface, and temperature. The simplest mathematical model that explains the coverage at constant temperature is Langmuir absorption model. It is based on a few basic assumptions. First, adsorption occurs on certain number of sites. Second, each site absorbs at most one adsorbate. So, each site has only two states, empty or occupied. Third, all the sites are identical and independent of each other. That is, the adsorption rate on every empty site is a constant. The desorption rate on every occupied site is another constant. Based on the assumptions, the adsorption-desorption process can be abstracted as a reversible reaction. Here, A is the free molecular entity. S is the site on the adsorbent. As is the adsorbate on the site. The adsorption is a second-order reaction because the free molecular entity must collide with an empty site to be adsorbed. The rate of adsorption is proportional to the product of the concentrations of free molecular entity and empty site. In gas phase, the concentration of molecular entity is proportional to its partial pressure. The concentration of empty site is proportional to 1 minus coverage. The desorption is a first-order reaction. The rate is proportional to the concentration of the adsorbate, which is proportional to the coverage. At equilibrium, the adsorption rate is equal to the desorption rate. It is an equation about coverage. The coverage at equilibrium can be solved. Define P0 to be the ratio of the desorption rate constant to the adsorption rate constant. Then, the coverage has a simple expression. It is known as Langmuir adsorption isotherm because P0 is a constant at certain temperature. The plot of Langmuir adsorption isotherm is shown in the figure. The coverage increases with pressure. Consider two extremes. When pressure is low, the coverage is proportional to pressure. It is an analog to Henry's law. Here, the adsorption size can be regarded as a solution, while the adsorbate is the solute. When pressure is low, the solution is dilute. On the other hand, when pressure is high, the coverage approaches to unity. The adsorption sites are saturated by the adsorbates. Some characters of heterogeneous catalysis can be discussed with Langmuir absorption model. For example, consider a simple reaction. The reactant is in gas phase. It adsorbs on a catalyst surface and converts to the product. The product then desorbs from the catalyst surface. For simplicity, suppose all the steps are first order. At steady state, the coverage of adsorbed reactant is a constant. So, the rate of absorption is equal to the rate of conversion. Pay attention to the concentration of empty site. The coverage of adsorbed product is also a constant. So, the rate of conversion is also equal to the rate of desorption. From these equations, the coverage can be found. The overall rate of reaction is the rate of conversion. Consider three extremes. When the partial pressure of the reactant is low, or the adsorption is slow, the coverage of the reactant is low and is proportional to its partial pressure. The overall rate is also proportional to the partial pressure of the reactant. Thus, the overall reaction behaves like a first-order reaction. Its rate is limited by the coverage of the reactant. For example, in the electrochemical reduction of proton on gold surface, the adsorption of hydrogen on gold is so slow that the low coverage leads to a slow reaction. When the rate of conversion is very slow, the catalyst is saturated by the reactant. This phenomenon is called the poisoning by reactant. The rate of reaction is limited by the rate constant of conversion and is independent of the partial pressure of the reactant. The overall reaction behaves like a zeroth-order reaction, such as the decomposition of ammonia on tungsten. It is because the formation of the triple bond of nitrogen is very difficult. When the rate of desorption is very slow, the catalyst is saturated by the product. This phenomenon is called self-poisoning. The rate of reaction is limited by the rate constant of desorption and is independent of the partial pressure of the reactant. The overall reaction behaves like a zeroth-order reaction. For example, in the electrochemical reduction of proton on nickel surface, the adsorption of hydrogen on nickel is so strong that the slow desorption leads to a slow reaction. The Sabatier principle is a qualitative concept in heterogeneous catalysis. It states that the interaction between the adsorbate and the catalyst should be just right. That is, neither too strong nor too weak. If the interaction is too weak, the reactant will fail to bind to the catalyst. On the other hand, if the interaction is too strong, the product fails to dissociate. For example, platinum has just right interaction with hydrogen. So, platinum is the best electrocatalyst for electrochemical proton reduction. In contrast, gold has too weak interaction, while nickel has too strong interaction with hydrogen.